So hi, I'm very happy to be here, and it was a great introduction by Radhika because I'm going to be talking about bio-inspired robots, as she did, and robots that move, not necessarily do structures, but move. And the point here is, how do people try to control? How are they effective in trying to supervise and control these robots if we're going to be using them in applications? So the overview is I want to start with some issues in control, supervisory control of robot swarms, and then control methods. And then basically I want to talk about the two projects that we had, or two papers. Leader-based control, as the first physical timing. And so the key idea that we have had for some time in our lab is to really look at the control of humans as a computational complexity type of thing, but taking into consideration the complexity, the cognitive complexity of the human control. So if we have robots that operate independently, then in order for a human to actually control n robots, they have to do n actions, right? Because I need to interact with one, I leave the other ones unattended, so to speak, and then I have to repay after I interact with that one. Right now I have to switch my attention to the next one, and then after that I also need to switch my attention to the next one. So what happens is that the cognitive complexity of the human grows linearly with the number of robots. Every time I add one, I need to actually pay attention to that. Okay? And so in other work that I'm not going to talk here, we have devised scheduling and tested scheduling regimes for actually doing this operator attention. And the point is not just to devise the algorithm, but actually to test do human operators then obey this. So there are two aspects when you are dealing with human supervision. You can have the algorithms as an engineer, that doesn't mean that these algorithms follow. So you need to do both the algorithms and then also test. So this is some of that work. Now, if you have robots that are highly competent, in other words, they can do planning or plan instantiation, they have roles, role allocation, and so on and so forth. Now, the issue is that in conjecture, that really it's very complicated, because if they do an optimal plan, an optimal PSP kind of thing, the human operator may not be able to understand what they're doing and actually may harm actually the cooperating robots instead of helping them. As a matter of fact, we have done some experiments with human in the loop for distributed rendezvous, for coordinated sensing and so on. And what we found is, first of all, humans were not capable of keeping track of these things for more than 3 or 4 of these variables. And second, that they were really maybe doing harmful things. In other words, we need to let them harm. But that's another piece of work that I just mentioned. So what I'm going to talk about today is what we call the O1. In other words, constant complexity in terms of human operator cognitive overload, cognitive load, in the sense that if I have a swarm that autonomously cooperates, and it is very simple, then what I can do is actually, with one input, I can actually control it. Say, go here. And then all of them, because they're doing fish, that they cooperate. So I don't care whether I had 100 or 1,000. So that was the O1 idea. And so here, I've heard talk before, so I don't need to really repeat that. We can store robotics. And the point is that we would like to actually use those things to, for example, exploration in oceans or in large-scale disaster relief or in other applications. So now why would we like a human control or to have supervisory control? When we say control, and they have their simple control laws, so when they move, so radicals work was more in terms of stigmatry and so on, doing structures. Now, if you have schools of fish and so on, what happens? So the basic idea of these simple control laws is the following. First of all, if the robots are far away from each other, you want them to attract, so to keep the swarm coherent. If they are very close to each other, you want them to repel to avoid collisions. And then the in-between is kind of the alignment or zone. So if you think, I have one robot, I have a radius of repulsion, and then a radius of attraction or coherence. So now if I have that, why do I need a human to do something for these robots? Well, first of all, to recognize and indicate shortcomings of autonomy. So if they don't do what they're supposed to do, like frankly we're saying, well, it can go away. In a lot of these applications with the moving robots, if you do the wrong thing, if you have the wrong input, they may split into various, instead of having one cohesive swarm, you may have different components, connected components, and they split and move away from each other. Another one is to convey changes in intent. So if you are thinking about this swarm that is going to be doing some exploration, now suppose the human knows that here is a more interesting place for them to explore. Well, how do I tell them that? Because otherwise they will just follow their own, what we call natural goal, right? And autonomously will just go there unless some current or whatever, may direct them otherwise. And so we utilize information accessibility. So what levers are there? What can we do as designers? We can choose an algorithm, in other words, change the algorithm, or change the behavioral parameters, or specify triggers like beacons and so on. We've done some work with that. Or control particular members to influence the rest of the swarm. And these members are called levers. And so in this particular work, I'm going to talk about one particular study where we have the so-called explicit leadership versus tacit leadership. Because in the literature in particular, there are advocates that say, well, if the fish work this way by taking the average, so how do these swarms in general work? What they do is each of the members of the swarm looks at its neighbors, and what they do is they take an average of the heading and of the heading in particular, or velocity. And so then they look at that, or their neighbors take the average, and they substitute that for themselves. And that's eventually all of that kind of the line. So they do local consensus basically. So in the literature in general, these have been studied this way. And what we looked at is this tacit leadership. So if you give them a control signal, what happens is for the signal to propagate, it takes a long time. Okay. So we thought, well, how about if we had a method in what we call explicit leadership? So the human influences the swarm by selecting one or more leaders and giving the particular values. So for example, particular heading, particular goal, and so on, that the human wants to specify, because now this is the population. Okay. These values are then propagated, but they are tagged. So in other words, if I am a member of the swarm and I receive a message, that is tagged, I recognize that as, oh, okay, now I need to align my heading according to what the value of that message says, rather than doing the local messages. So that's the leadership. And then the tacit leadership, specifying the value, this influences the propagation to the normal consensus. So in the tacit leadership, the human injects the input to one or more leaders, but the point is that nobody knows that these messages are produced. And so the propagation method then, the explicit leadership, is, as I said before, it's fast directly distributes messages, and in general, what observes, if one does the algorithmic part, is that the convergence is faster, it is more, the behavior is more predictable, but there is low communication, noise tolerance. So the point then is, okay, these are the algorithmic properties, so they need the consensus in terms of the tacit leadership, and there is high communication, noise tolerance, and slow first. So the point is, algorithmically, this is untrue, but the point is when you have people try to use these methods to control the swarm, then what is the result? So we did a preliminary comparison, okay? And also we want to see what is the convergence time, the robustness, and graph structure, and so on. So we did the following experiments. Repeated measures with 18 participants, The one was the flooding consensus and the no error condition or error condition. We're injecting error. And so this particular thing, hopefully, these are. So the idea is that the human is controlling through a virtual joystick here, that is the heading and the direction. And you see the robots here that get the messages. Here is a goal region. When 50% of the swarm robots get into the goal region, then another goal appears somewhere else. So the idea is, what is the best way for the human to direct the swarm so that the most number of goals gets visited? That was the performance criteria. So the goals reached, what we see is that in the condition of the flooding, in other words, the explicit leadership without any error, the greatest number of goals was achieved. With error, the number of goals was less, but in the consensus, very few goals previously were. Then, of course, in the error condition to the consensus was even less. So now one would also want to see how these parts or how connected they're going to remain. So in terms of cohesion, there could be a difference. And so what we find here is that in the diameter, the measure in how large the diameter is gives us this coherence measure, and what we see is in the explicit leadership in general, they are less coherent. Okay. The diameter is bigger, the explicit, whereas in the tacit it is smaller. That means the swarm is more compact. So the point is that one could look at applications and say, if I have confined spaces, or if I have particular applications where I do need to keep the swarm over here, and maybe I should use tacit leadership, and other ones when I want to spread out more and so on, but converge faster, I would use explicit leadership. Now, so these are the advantages, disadvantages that we say. And here we have, we don't have 1,000 because we're using turtle plots, but this is just an experiment with the tacit leadership to actually show that yes, indeed, so you can go and you can 10 or 15 of those and we do this experiments, and then the person was actually giving the commands to the leader here, and showing his doing consensus, and they're going to go in, follow the leader, and go into this error work. So that's doing that. For the sake of time. And so the second then topic that I want to talk about a little bit, the second study, is, okay, so we talked about explicit and tacit leadership and other types of things, but the point is, what is the influence of the timing of the control inputs? So what we have found is, of course, one could say, well, I could do an optimal control thing and so on. The point is that, of course, mission goals change in the middle, and so we cannot really use design and optimal control things because we don't know what time controls and so on to device. So, and one of the things that we have looked at, we have found out in human experiments with simulated swarms, shows that delaying the human input when another goal appears, delaying the human input rather than immediately saying, trying to grab direct the swarm to go to that other goal, could improve performance. And so we term this phenomenon neglect benevolence, as opposed to sort of I thought it was a little bit semi-joking, because in HRI we know the notion of neglect tolerance. So neglect tolerance says that if a robot is left unattended, its performance is going to deteriorate and it begins to interact with the human operator. Okay. So by opposition, neglect benevolent means, well, if you leave the robots to themselves, they may be better off than immediately jumping to control them. And so the point is that delaying the human input may be beneficial then when the performance objective will be minimize time or have the robots have some deadlines. And so, as we said, what is the best time for a human operator to apply an input or robot SOAR? And because we conjecture that it would be difficult for humans to actually be able, even for linear systems, let alone for nonlinear system, to actually conjecture themselves, when would be the best time. Then the idea was that it's formalized neglect benevolence and input timing, but also we would like to see whether humans are able to approximate this. And so here's an illustration just in state space. In state space, I just visit the natural mode. So you can see here that if I give the input here, I have a longer trajectory if I give the input here. When I go change. So this is so what we are able to prove actually is that even LTI systems are neglect benevolent. We will go to the study, I won't say much about that. The curves, the neglect benevolence curves in general are like this. Okay, so if I really immediately the input and not, so you see here the dip, that says here the dot. Now, what we want to do is to be able to study whether people are able to approximate this optimal input time. And so, what is the point here? The point is, if I want, as a human operator, to approximate the time to do the input, I need to, first of all, have an understanding of the state of the swarm, and second, have an understanding of the potential effects of my input. Now, to have an understanding of the swarm, we know from psychology, there's the so-called Gestalt perceptual principles, that if one has common heading, common velocity, common fate, people can perceive that even in the presence of a lot of noise. Now, in our experiment, we use the formation change experiment where the headings or velocities may match. So we took away this kind of, there is still some perceptual information, but not really as regular as what we see in psychology. And so the idea is that here we are, the initial configuration here is a line, and the final configuration will be a circle, and they always start in some kind of random position and move. And the point is that the person needs to inject an input to see whether they, so if the input is too late, sometimes it doesn't first work. If the input is too early, it may take a long time. And so, and the person really be able to approximate. And so, we had for participants, we use participants issue command. In the transient state, as the robot is going to go towards one goal, I issue a command for it to go to another goal. So from one configuration, if the robot swarm is going to one configuration, I issue command to go to the second configuration. And we had two conditions, the AD condition and an AD condition. The AD condition will also show that these little lines that became longer and shorter as it is not a very simple relation between approaching the goal and the line length, but it is some kind of every approximation. But the people were able to see these lines in the AD condition. And so the results said that main effects were found between the AD and AD condition. In other words, that the people in the AD condition were able to perceptually see that and be able to do better than the people that did not really, the display was not really aiding them. And average preceded the optimal time. So they were very, so the goal appeared, the new goal appeared, and they were very impatient to actually impart it. They didn't do it immediately, but they were very impatient to impart it. And so, that's my last slide, I think. So, in summary, what we looked here are two things. That one is how can humans control what are the best strategies, or some investigate some strategies for humans to control small robots. And second, what is the effect of timing of human input? And third, whether humans were able to approximate the optimal time. And we found that, okay, they did not do the optimal timing, but they could somehow approximate. And these are preliminary results. They will be presented in page 11 in March. Thank you. Yes?
I was thinking there are lots of also game environments where a gamer is sort of moving around groups of individuals like a vibration or an army or something. From that sort of experiments of many, many people, are there particular ways in which you think people are more likely to perceive the purpose of the swarm or how to affect it, or do you?
Well, you see, the thing is that in this other, so it depends on what the control laws are, right? Because, I mean, that's the whole thing. So it's very unintuitive for people. We've done many experiments before these ones with the timing and so on. It is very unintuitive for people because you have this thresholding of the areas of repulsion, the areas of attraction, and so on, your system is going to be here. And so your effects are going to be here. So what we have seen is if they input, for example, in simulation, but also in experiments, human experiments, are more difficult to actually tease apart, what's going on in the person's mind. That's why also I mentioned these conventions. Is that what we've seen is that if you put the input in the either where they may split actually the robots, so they will never accomplish the goal, and they go away, or you may have one that is sitting there and it's not really coming. And so it's really a very unintuitive behavior. That's why we were a little bit surprised actually, but with the alien display and so on, trying to see that we could somehow get some kind of an idea. There are other experiments in psychology, for example, of how we will try to get an idea of dynamical systems. What is of importance here also is that even if you have subjects that are engineers and they know the dynamical equation, it doesn't help.
Well, I was thinking more kids where they learn, they play, and
Yeah,
it's unintuitive, they seem
right.
to be better.
But yeah.